Is speak English? Okay. Okay, let's start. Let me start with some little motivation. My talk is about some discrete model, but I would like to introduce first some continuous models just for motivation. So consider the Euclidean space n is equal to 1 to a natural number, and consider the domain omega sub n, which is a domain here, and it's just the set of points with strictly decreasing coordinates. But given an element x in this domain, I will regard it as a particle configuration on the real line. So this is the real line, and these are point particles.
So x is not homogeneous in R.
Yes, of course, but any point with distinct coordinates and strictly decreasing coordinates can be viewed as a point configuration on the line. One particle here, one particle here, and the last particle here, okay? So this, and I would like to introduce next, let P of omega be the set of probability measures So given a probability measure here, we can view this point configuration as a random object. In the presence of probability measure, we can interpret a particle configuration as a random object. And what is this measure? A family of examples comes from random matrix theory. It proposes the following definition. We have some normalization constant, just to get a probability measure, times a product of some functions. I will call it a weight function, and times the van der Monde determinant this quantity is strictly positive because of this assumption, and raised to power beta. Beta is assumed to be a parameter. So this is some family, some possible choice of my measures. The motivation comes from random matrix theory. For instance, if you take beta is equal to 1, 2, or 4, and say the weight function of a form then this distribution can be obtained as follows. We consider the space of Hermitian matrices. Hermitian matrices. Over one of the three possible fields, that is real. So this Hermitian means symmetric, complex, which is just conventional Hermitian matrices and quaternions. And we equip as a vector space, it is a real vector space, we can equip it with the standard Gaussian distribution, and next we take a spectrum of such a matrix, and the spectrum gives us a particle configuration, and in the presence of some probability measure, say Gaussian distribution, you just get this kind of distribution. So this is just a motivation. Of course, if beta is an arbitrary positive number, there is no such construction, but still, in random matrix theory, it is common to consider this model. But my talk is about some discrete versions, or some discrete analogs of this picture. So in my talk,
Just from the term, C corresponds to beta equal to 2.
yes,
And this is normal.
yes, exactly. Yes, exactly. Now we can forget about this. And I would like to discuss a discrete case. So, in my model, the real line will be replaced by some discrete set. I will specify it in a moment. What is this discrete set? I call it two-sided Q lattice. By definition, it's a subset of a real line of such a form. What is this? By definition, Q is a positive parameter between 0 and 1, and this is just something like geometric progression which goes to the left and accumulates to 0 and to infinity. So we have here 1, Q square, and so on, and Q minus 1, and so on, and likewise on the left. More generally, one can introduce two extra parameters, zeta plus and zeta minus. One is positive, another is negative, and just add here this is some minor extension of this lattice. Okay? So my object is this lattice. And remark, as Q goes to 1, this lattice approximates the real line. So this is some kind of, say, quantization. There is no physics here, but, say, quantization, discretization. Okay? Now I need one more parameter, T, which is the second Macdonald parameter, which is assumed to satisfy the same constraints. But to simplify the picture, just to simplify the picture, I will suppose that T is equal to Q raised to power tau, where tau is a natural number. That is 1, 2, and so on. This is just to simplify. Things becomes more complicated if we assume general T. Throughout my talk, I will assume only this constraint. Okay? Now the question is what to do next. One could think that, okay, one can introduce some weight function on the lattice and the van der Monde, but this kind of definition does not work in some sense. We need some more delicate version of this object, which I define now.
But it depends on what do you want. So you did not tell us what you wanted from this.
I would like to explain step by step. Okay, so instead of this Vandermonde raised to power beta, I will introduce a bit more complicated object, which I denote as follow. So this is a product again over I and J. And next we have a product over M equal 0 to tau minus 1. Tau is a natural number, okay? And I write some Q version of this object. So if Q is equal to 1, and sorry, I need some sign factor, just to make this product positive. If Q is equal to 1, then we get just this 1 with beta equal to. Okay. Yes, yes. If tau is equal to 1, which gives us exactly the squared Vandermonde.
You said that the naive formula doesn't work, but it is.
Yes, in this particular case it works. Thank you. In this.
Also beta. So you raise the Vandermonde to the power beta also.
Yeah. Beta is twice tau. It's not a theorem, it's just an experimental fact. It's just an experimental fact. I cannot develop a theory, a good theory, with. Let me continue. I'm sorry. Okay, exactly. I'm sorry, I have to impose on you some collection of definitions. And now I would like to explain what is the weight function. So the weight function will depend on n, on q and t, and a quadruple of parameters, alpha, beta, gamma, delta. But this is a beautiful formula. I will try to explain why it is beautiful. What is this? First, please ignore for the moment these factors. Okay? What is this symbol? This is the Q Pohammer symbol. The product is convergent because of this constraint. Why such a definition? I can't explain just now why it is good and why it is beautiful, but I would like only say that this Polynomial symbol is very close to the gamma function. But indeed, there is the definition of the Q version of the gamma function, which is as follows. Some factor, but this is just a constant, which depends only on Q, and Q to Z, and some compensation factor. Okay. And as Q goes to 1, this function of Z approximate the classical gamma function. So in fact, what is written here is the product. Essentially, this is a product of two Q gamma function in the numerator and two Q gamma function in the denominator. This is a very good expression, in fact. I will try to explain maybe at the end.
But just in terms, you have 6 parameters.
Ah?
In total you have 6 parameters. Alpha, beta, gamma, delta.
Okay. This is related to coordinate polynomials, which is okay. There is some links to coordinate polynomials. You are right. But now I can state the result. So I will assume that some constraints on alpha, beta, gamma, delta. I need them in order to make this function positive. For instance, the possible conditions are as follows. They are conjugate and non-real to avoid singularities. And likewise are conjugate and non-real, and some extra mild constraint, which is neat. Okay. And then I define a probability measure, what is my omega sub n? My omega sub n these are n particle. I will explain. On my lattice. So n particle is clear. What means tau sparse? Tau sparse means the following. So I have, look at my lattice. These are the nodes of my lattice. And look at this expression. You see that this quantity vanishes if two particles are too close to each other because of the very picture. So tau sparse, in my definition, means that between any two particles there are at least tau minus 1 holes. Of course, if tau is equal to 1, there is no condition.
Can just say that if they are more close,
Yes. Yes. Okay. This is exactly what I would like to say.
Like Vandermonde excludes the coinciding.
Yes. Yes. Exactly. Exactly. So I define a probability measure by the same formula. So now this set is a countable set. This set is not a continuous space, it is just a countable set because we have a countable set L and endpoint configurations. And I define the measure with all these indices by the same formula, the normalization constant. It exists because of some extra condition on the parameters. The product of the weight of the weights and times my deformed Vandermonde so this is some probability measures. Okay? But now the result. The result is as follows. I need to introduce one more object. So omega infinity is just all infinite. On my lattice. Sorry?
What means all?
Infinite. So infinite just means that it must contain infinitely many particles. This is one condition. And the second condition that the configuration must be bounded. What means bounded? It should be contained in some finite interval of a real line. But it can be infinite because the particle it should accumulate to zero. So this is some space. It is not countable set. It can be equipped with a natural topology, and in this topology, it is like a Cantor set.
What is that also negative part of the real line?
I will explain. I will try to explain. It is another experimental fact. Huh? Tikhonov topology. No, not Tikhonov topology. No. I'm some kind of some kind of topology like Tikhonov topology. So bounded.
Bounded means that you remove infinities, yes?
Yeah. Yes.
Minus infinity,
They cannot accumulate to plus or minus infinity. Cannot. They accumulate. Cannot should because they are infinite. They can accumulate from one side only. It's possible. So the theorem is as follows. So fix alpha, beta, gamma, delta, q, and t fixed, and let n go to infinity. And there exists limit which is a probability measure which lives on this space. So the main result, if you want, the existence.
Meaning of this limit, you change not only the measure but also the space.
Okay, I understand. Okay. But in some reasonable sense, in some reasonable sense, there is a limit.
But something converges, like some calculation of some absolute.
Of course. Yes, of course. We can say observables. Okay. So take a window, some interval which is separated from zero, and look at the, say, number of particles inside it. This is an observable. Or another observable is just the indicator, which is a function which gives us 0 or 1, depending on where there is a particle or not. This is a kind of observable. So this is convergence on an appropriate set of function observables. Okay? So this is the result, the existence of such a limit.
And to count parameters, before when you define the L, you have parameters zeta plus and zeta minus.
Okay.
You have still independence on the.
There is, in principle, all this picture depends on zeta plus and zeta minus. In some not very substantial way. Sorry?
No, a particular case you consider you started with was when these two parameters were
Plus minus 1.
So the dependence on them is not essential.
Not very essential. In fact, what is essential is the lattice itself. So, for instance, nothing changes if zeta plus or minus is multiplied by some power of q, because this does not affect the lattice. This is just a mean to fix some lattice, which consists of two geometric progressions. Okay? And what can be said about this measure? The particular case is tau equal to 1, and this is our work with Gorin. And in this case, we calculated. This is so-called determinantal measure, which means that the correlation functions in this case can be computed exactly. So in some sense, this is an integrable case when correlation functions not only can be computed they are given by some determinantal formulas involving some Q hypergeometric functions. And moreover, there is some recent paper by Cuenca, Gorin, and myself, which implies in particular that this limit measure is a diffuse measure. What means diffuse? Diffuse means that it does not have atoms. Diffuse measure. Diffuse measure. Measure no atoms.
It means that measure of any one point set is used, right?
Exactly. But for general Q in T, this is in some sense, I think, non-integrable picture. I'm unable to calculate some correlation functions, which is just the case in the continuous case of arbitrary beta. it is very difficult to calculate correlation functions, except the case 1, 2, and 4. Okay. In some mysterious case, it is related to the fact that we know only 3 fields: real, complex, and quaternions. No other fields. This is not an explanation, but some indication of the difficulty. Now I would like to explain the mechanism of a proof, which I believe is also of some interest. How to prove such kind of results. In our situation, tau equal to 1, we can use correlation functions. We can compute it for the n-particle model and take the path to the limit as n goes to infinity. In this more general situation, we don't dispose of this possibility, so we need some other technique. What is this technique? I will try to explain. This technique comes from representation theory. I will try to explain now some abstract formalism which works in this situation. What is this formalism? So imagine we have a tower, some countable set. So forget about my definition of configurations with some abstract countable set. And actually we have some tower. Infinite tower. What are these dash arrows? These dash arrows are what we call stochastic links, or simply stochastic matrix. What is this? I recall the definition of a stochastic matrix. Stochastic matrix is a matrix. The entries are non-negative, and all the row sums are equal to 1. So assume we have some sets, say A and B. The rows are indexed by element of some set A, and the columns are indexed by elements of some set B. And we have some matrix with the entries lambda, A, and B. So the condition is the entries are non-negative, and the sum for any A, the sum over B is equal to 1. How to interpret the stochastic matrix? A stochastic matrix defines what can be said transition probabilities. Or some generalized map. We would like to generalize the notion of a map from A to B. An ordinary map assigns to any points of any points A some points B here. A generalized map assigns to any points a probability distribution on capital B. So this means we don't know exactly the image of A, but we have some probability distribution. So A is maps into capital B. Its distribution is given by the row number A. Okay? So this is in some sense a generalization of the ordinary map. But even despite the fact that it is not an ordinary map, it is a good object. So if you have, I will denote it just to emphasize the fact that it is not an ordinary map. I will use dash arrow. So I will regard my lambda as a generalized map. And as such, it induces a map from probability measures to probability measures. It is given as follows. Given a probability measure here, we assign to it the probability measure here, which is given by the formula and in the inverse direction, lambda also induces the map from functions on B to functions on A, just by dualization, if you wish. Okay. So I return to my picture. I continue to introduce some formalism. So assume that we are given some sequence of countable, or maybe even finite sets, which are linked by certain stochastic matrices. So I assume now let me reproduce this picture.
It will be certain just.
They are different because these sets can be arbitrary. They vary. So we have some set here. And so on. And we have some matrices which I will denote as follows.
Can we come to the generalized maps?
Yes, of course. This is just multiplication of matrices. So in my picture, this is a matrix. This is a generalized map from this set to this one. And now it is possible to define what can be called the boundary. I will call this data projective system. Projective system, which consists of a sequence of countable sets together with some stochastic matrices. So I call this data a projective system. And given an arbitrary projective system, one can define an object which I call the boundary and define it omega infinity. It can be introduced in various ways. If you wish a category theoretic definition, it is just the inverse limit of this object in the category where the objects are Borel sets. And maps are Markov kernels. Markov kernels is just a generalized map in my sense. It assigns to a point of one set a probability measure on another. So one can give an abstract definition in the style of a category theory, but one can give also a constructive definition of this object. So by the very definition, this object is some canonical object, which is generally speaking, it is not already a countable set, but it is some space with a sigma algebra, a barrel space, and there are generalized maps making the whole diagram commutative. So there are some Markov kernels or generalized maps making the diagram commutative. And this is a kind of universal object with this property.
This map, do they have the sense that you integrate over one particle or map and get n-1? Or
There is no such interpretation because in this formalism, this is not a set. In general, it is not supposed to be a set of configurations. It's just an abstract set, an abstract countable set. Let me give an example. 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 The example is the Pascal graph. This is the Pascal graph, or which is written in a bit unusual way, but omega n is just the set of pairs k and l such that k plus l is equal to n. So this is level number, say, 0. This is level number 1, level number 2, and so on. Okay. And there are transition probabilities given a point here. It can be mapped with some probability to the lower level with the probability as follows. And the probability from k, l to k, l minus 1 is equal to l, k plus l. So there are transition probabilities from each point to two neighbor points of a lower level. And what is the boundary in this case? The boundary in this case is just the closed unit interval. This claim is equivalent to some classical results, the definitive theorem or the Hausdorff moment problem, and it is also closely related to Sergei Bernstein or to polynomials. So this is a mixture of classical results. So informally, the boundary points is a way to go to infinity along this graph. But something similar happens in very abstract situation, like this. Okay? Why I need this picture? I need more definitions, I'm sorry. I need some abstract result, which is as follows.
Right now, when we consider these maps with the different formulas, you don't need neither E nor W.
No, no, no.
You can forget about all this.
Absolutely. Absolutely. So
Like writing the real number into
Edic. To Edic. No, I don't think it's a good idea. I don't. Okay. So assume what we have. Assume that we are given some sequence of measures, probability measures, and we say that this system is coherent a sequence of probability measures is said to be coherent if it is compatible or consistent with the stochastic links, which means that for any n I recall that given a stochastic link between two spaces, we have a map from probability measures here to probability measures here. Okay. So the condition is that my measures must be consistent with the stochastic links. This is my assumption. But now the result, an abstract result, which says if such a sequence is coherent, then it gives rise to some probability measures on the boundary. There is one and only one probability measure on the boundary such that it is compatible with these generalized maps, meaning that so my result is deduced from this theorem. I use this abstract result, but I need some concrete stochastic links in my situation. So now I return. Sorry? In this example? Where? But it depends on measures on the levels. There is one-to-one correspondence between arbitrary probability measures on the boundary and arbitrary coherent systems. Okay.
Coherent system is the set of measures on these omega n's.
Yes. Satisfying this relation. This is an infinite system of linear equations. In this picture? Yes, there are, but I would like to, of course there are some, okay, but let me continue. I would like now to explain what happens in my situation, where these omegas are configuration spaces on the lattice, and y are Macdonald polynomials here. So I return now from this abstract setting to the concrete situations. So again, this is now tau sparse and particles configurations on my lattice, two-sided Q lattice. And I want now to construct some stochastic matrices. So I need some matrices so X is an n-particle configuration, Y is n-1 particle configuration. And what is this quantity? How to define this? Now I need Macdonald polynomials. So let me introduce Macdonald polynomials now. Should I give a definition of Macdonald polynomials? Yes, I should. Okay. Okay, but I think that many people know, and better than me, but nevertheless. Let's consider the ring of polynomials in n variables which are symmetric, that is invariant under permutations of a set. This is the symmetric group in n letters. And there exists, if we fix two Macdonald parameters Q and T, and there exists a homogeneous basis, of polynomials, of symmetric polynomials. In my notation, they are denoted as follows. Nu is a partition This is a sequence of non-negative integers which are weakly decreasing. And these are, I need this just to emphasize the role of the number of variables. This is a bit non-conventional notation. So this is my polynomial, the Macdonald polynomial. It depends on Q and C. And okay, they are, it's not easy to define them directly, but one can impose some characteristic conditions. These characteristic conditions are as follows. First, we have some kind of Cauchy identity, which means that the sum over all nu, this is my notation for partitions of length less or equal to n. We have some factor which depends on nu and q and t. This is another collection of variables, and now the result is as follows. Okay, this is some condition. And another condition, the second condition, is some kind of triangularity condition, which means that my polynomial looks as follows. This is the leading term, the leading monomial, plus low terms, say in lexicographic order. The combination of these two conditions can be viewed as a characterization of Macdonald polynomials. It's not without knowledge, but next it can be computed. This is a fine theory, but okay. But in the case Q equal to T, there is a simple formula because we get exactly the Schur polynomials. So there is an exact formula. So this is a well-known definition of Schur polynomials, and it turns out if Q equal to T, we get exactly the Schur polynomials, and Macdonald's polynomials are a certain very very delicate two-parameter deformation of these polynomials, but still they form a homogeneous basis. It's impossible to say more in this talk.
Which of their properties is the most important for you?
This one probably is, in some sense, the best property, which is really used in computations. But of course, this is also important. But there are many other properties. For instance, the Macdonald's polynomials are common eigenfunctions of a system of commuting Q-difference operators. And there are some other properties as well. So I return to my problem. My problem is to define these matrices. And it turns out that they are closely related to Macdonald polynomials, and in fact, they can be characterized in terms of Macdonald polynomials as follows. I recall that given a generalized map, which is given by some matrix, by some stochastic matrix, we have a dual map. Functions on this set to functions on this set. And now the result is as follows. I'm sorry, because in fact, I would like to tell you about a work which contains many computations. I am unable to give some proofs. I would like only to indicate very roughly some ideas, just to get you to understand some flavor of what has happened here. So the theorem is as follows. So there exists a unique stochastic matrix, which is characterized by the following properties. When we consider the corresponding maps from functions, then you have the following. for any partition with at most n minus 1 coordinates. What this means? What is this? This is some renormalization of Macdonald polynomials. Some renormalization. We just want to introduce some numerical factor here. It's not very important to explain it, but the essence of this formula is that, roughly speaking, as a map from functions, this stochastic links preserves Macdonald polynomial, slightly renormalized. Okay? And it. Yes, of course. Yes, of course. Yes, of course. The idea is as follows. For any configurations, the formula reads as follows. Yes, I know, but it's complicated. I know. But this characterization which really works. Not the exactly formal, not the exact form. The exact formula is useful, of course, but this characterization is the key.
You have to change normalization of Macdonald polynomials just to make this lambda satisfy this.
Yes, exactly. We need some normalization. I don't want to explain all the technical details. It's not very important.
For how many lines we have non-zero matrix element lambda xy?
Okay. One can say that vanishes unless x and y interlace. Roughly speaking, which means this is my lattice. We have this is 0. Something like this.
So for Q equals T, it's just a differentiation test.
Almost. This is true. This is half true. This is half true. This is half true because we have. Because we have positive and negative coordinates. If you neglect the negative part, then we get exactly the Gelfand-Zetlin picture. So this is the end, but I would like to maybe to add a few comments. First of all, the result actually holds for arbitrary Q and T. not necessarily to q to some natural power of q. But the things becomes more involved in this situation. So this is the first comment. And the next comment is just about Gelfand-Zetlin. Actually,
Everything is based on this idea.
sorry?
Everything is based on this idea. Now, the sum of the y's, lambda n minus 1 and xy times p is equal to.
Yes, I will. What is the question? This is the characterization. No?
I mean, so this identity holds for any qt. Or what?
QT are fixed. I would like to say that we may assume T arbitrarily. But things becomes more complicated. The interpretation in terms of a lattice becomes more complicated. But still, the matrices can be defined, and the whole picture holds true. The the last comment is about the Gelfand-Zetlin and the relation to representation theory. So let's assume that Q is equal to T. So assume that we have tau in my notation is equal to 1, which means that Q is equal to T. And tau sparse means nothing. There is no condition now. And I would like to maybe to add that what happens now. So my weight function alpha, beta, gamma, delta, q. If you take x equal, if you take x positive and represent it in this form, that we essentially get something like this. And I assume that just assume that they are represented in this form. So just assume. I would like just to show the formula. And as Q goes to 1, you just get ordinary gamma functions. Okay. Now, so assume that we have, say, lambda n plus is just the configurations on L plus, which say Q to Z. In this situation, as Q goes to 1, my measures in the limit, here n is fixed, but Q approaches 1, but in the limit my measure is concentrated. But what is this? This should be interpreted just as the ordinary lattice via the map, via the correspondence. So neglect this interpretation and just view this lattice with geometric progression or multiplicative version and identify it with the additive version, additive lattice of all integers. Okay? So we can view our measure. So what I would like to say, in the limit, the measure becomes concentrated entirely on the positive part. The negative part in the limit disappears at all. And what we get in the limit is some probability measures which comes from harmonic analysis on the infinite unitary group, some old paper by Borodin and myself. But the mystery of this story is, if we want to deal with Q versions, we need to add the negative part. In some sense, we have to duplicate the Gelfand-Zeitlin graph. There is a natural one-to-one correspondence between sorry?
You keep the right side of the paper.
I don't understand.
Стирайте справа.
Не стирать или стирать?
Не стирайте. Вам
Нет.
нужна или просто...
Нет, она мне не нужна. Она мне не нужна. Consider the set of signatures, the so-called signature. This is Hermann Weyl terminology, or highest weight for the GLN groups. This is just a collection of integers which are weakly decreasing. To any lambda, we can correspond in particle configuration as follows. This is one of the possibilities. So we get some identification of a positive part on my configuration space with the highest weight of the unitary group. So the signatures are the labels of irreducible representations of a unitary group. Now I can explain the origin of stochastic matrices in the simplest situation without Q versions. We have unitary groups and natural embeddings. And we have dual objects. A dual object is the set of characters, or which is of irreducible characters, or which is the same, the set of irreducible representations or irreducible characters. Okay? So this is the dual object. In the simplest case of unitary group of dimension 1, which is just the unit circle, and the dual object is Z. For locally compact abelian groups, we dispose of the notion of characters, okay, of a dual group. If gamma is a locally compact commutative group, we can assign to it the dual group, which is the group of characters. And this correspondence is functorial in the sense that if you have a map from one group to another group in the same category of commutative abelian group, that we can dualize this picture. But what happens in this situation? These groups are no longer commutative. We still have the set of characters, but they don't form a group. There is no natural map. There is no natural map dualizing this embedding. Okay? But there is still a natural generalized map from this object to this object. So in the category of the so-called category of Markov kernels, there is a natural dash arrow from this object to this object. And how to define it? We just take an irreducible character, chi, and normalize it, that is, divide it by its dimension. That is, it is the function chi of G. G is an element of my group, and normalized by the value at the identity. Okay? If we now and so let chi sub lambda tilde is the irreducible character of a unitary group, which is just the Schur polynomial divided by the dimension. Now we have a natural restriction map. We can restrict it to the lower, to the smaller group, to this group. And then one can prove, it is an easy exercise in representation theory, that it can be written as a convex linear combination of characters and this is a stochastic matrix. The coefficients are non-negative because of the characters are positive definite functions on the group, and the row sums are equal to 1 because of a normalization. So in this situation, when we have embeddings, or more generally some maps between compact groups, we are able to introduce some dualization of these maps, which are given by stochastic matrices. This convex just means that the row sums are equal to 1. Convex linear combination, okay? So in this situation, there is a simple formula, some ratio of two van der Mon's determinants.
You are saying that this is the answer for omega n plus, right?
This is only for omega n plus.
And if you are want to say the answer for omega n, is there such a simple description? So now you have two irreducible representations.
There is no representation theoretic interpretation.
No, but here, this C is exactly the restriction from GLN to GLN minus 1.
Yes, exactly. But this works only for the restriction of my stochastic matrix to the positive part.
But if you avoid this class, then you have two representations, and there is no way to say how.
I don't know what to say. One can justify my definition, but from the point of view of orthogonal polynomials, the definition seems to be natural. This definition of the double Q lattice. It's natural. It's natural from the point of view of ASCII scheme of orthogonal polynomials. But from the viewpoint of representation theory, it's mysterious. It's mysterious. What is the mystery? The mystery is as follows. My measure on the level 1, in the simplest case without any Q, in the setting related to harmonic analysis, is closely related to some beautiful summation hypergeometric identity, which means as follows. Under some conditions on the parameters A, B, C, and D, there is a beautiful summation.
I think the summation is over n.
Yes, there is, I'm sorry, Di. There is some ratio of products of gamma functions on the right. A natural question is as follows. Okay, we have a beautiful identity which is called, this is one of Dugal formula. We can find it in the higher transcendental function in the very beginning of the first volume. This is a truly beautiful formula, but okay, we know what are the Q gamma functions. What about a Q version of this identity? And it turns out that there is no direct Q version of this identity. But there is a two-sided Q version. In the most natural, seemingly natural version, we only have to replace an integer L with this one. Okay? But it turns out that there is no Q version of Dugal formula on the positive part, but there is some version on the two-sided Q lattice. This is some indication of why we need this duplication procedure. Why?
The negative part disappears.
Yes, in the limit, if you take the true Q version of Dugal formula, in the limit, the negative part disappears.
What does it mean? Can you just explain how it disappears? That is the reason why you need this negative part, yeah? But how it disappears? So this identity you wrote now, the last concise, appears in the limit of this two-sided Q.
But it disappears in the very simple way. We have some this object, this is some multiplicative lattice, and can be identified with the disjoint union of two copies of the ordinary additive lattice. And we have some measure on this object, which depends on Q as a parameter. We can interpret it as a measure here, and as Q goes to 1, the mass of this set goes to 0. This is...
The measure is not on this space, it's on the space of...
Yes, exactly, I'm sorry. No, it's on this space, because I consider the case of one-point configurations for simplicity. So for me, it's mysterious. There is some work by Sato, some young Japanese mathematician, and he found some way of to interpret the Q boundary of Gelfand-Zetlin from the viewpoint of quantum groups. But if you want to consider some measures which are actually related to harmonic analysis, we need to consider this two-sided version and what is possible interpretation in terms of some object like quantum groups or something like this. I don't know. For me, it's a mystery. I ask some people, they say nothing. It's unclear. They are very different. They behave. You have to look at the definition of the Q per hammer. There is a great difference in two cases. Say Z is positive or Z is negative. For instance, if Z is negative, there are no zeros of these quantities.
So can we reduce this limit to rescale this?
No. No.
Technically, how it goes.
Hmm?
So technically, how it goes. You have terms which correspond to negative L or a negative Q power, negative part of the lattice, and each such term just goes to 0 or just becomes 0.
I forgot exactly the proof. I'm sorry. But the idea is this can be shown as follows. We ask about how to prove this limit transition and the fact that the negative part disappears. This is the question. But okay, this is just to compare the right-hand side of the identity, and we see that on the right of the 0 we have a pointwise convergence. We have a pointwise convergence, and the right hands also converge. And from this one can deduce, I think, that the left-hand side disappears because all the terms are non-negative. Something like this. But this is some technical facts related to asymptotics of programmers, nothing more. I'm very sorry something happens.